As always, I will start today by a mea culpa. I made a mistake yesterday. And I'm making a mistake right now. Inductors. So I need to fix my mistake before we move on. I always get myself talked into a circle when I'm trying to explain things and trying to concentrate, and no different to yesterday. So let's get back to kind of where we were. We have an inductor of value L, a resistor of value R. Although I said in our discussion yesterday, the inductor is going to have internal resistance too. So whether this R is a separate resistor or represents the total resistance of the circuit, I don't know, you guys don't generally write down these little things, but I think you probably should. Be mindful of what the problem states. Does the problem talk about the internal resistance of the inductor? If so, they're sending you a message. If they don't, then the assumption is that the internal resistance of the inductor is zero. And although that's impossible, pay attention. It goes back to this thought that we had earlier in the year about the difference between a real object and an ideal object. So remember, real batteries have internal resistance and behave in certain ways related to that internal resistance. That is not what we would expect in the ideal world. Same with voltmeters and amp meters. They all have these ideal circumstances. So if they don't tell you that the inductor has any internal resistance, it probably doesn't. You can treat the inductor as being just something that stores energy and doesn't have resistance itself. But remember, if you're asked about the ideal versus the real, be prepared to describe the fact that your inductor has resistance, and that resistance plays a role in how the circuit behaves. Yesterday I was saying we should do we had a switch in here too somewhere, and of course it doesn't matter where I put the switch. The switch is going to become much more important in this conversation when we finish our first example, so pay attention. We're talking about closing the switch at t equals 0, and at that moment, the current, there's no current in the circuit. We go to close the switch. Now, I want to start by backing up and saying I made a mistake yesterday. And I was afraid I was going to do this, but I got ahead of myself. Unless you have an object that is actively producing a potential difference, it always gets assigned a negative sign as a voltage drop. So when I began this process and substituted in IR for the potential difference across the resistor, and then went in and put a negative sign in here for my inductor, I was wrong. I was making a mistake. We still treat the inductor as a voltage drop, and that negative sign is unnecessary. And although I try to explain it, and I convince myself the negative sign goes in there, it's a drop of potential between here and here. So I treat it as a negative sign when it goes into Kirchhoff's law. I don't add another one for the explicit negative sign that's in the definition of inductance. That's already telling us that there is a voltage drop. That's what that negative sign is for. And it's not because I need to be reminded it's a voltage drop, because remember, there's not a voltage drop across the capacitor. There's not a explicit negative sign in Q over C for the capacitor, and there's not an explicit negative sign in IR for the resistor. The reason why there's a negative sign here, and I looked it up just to make sure I wasn't an idiot, is because it's based on the direction of the current. And therefore it's reminding you that this inductance is based on opposing the change in the current. We know on our setup that it's going to oppose the change in current because we're creating a system to do so. So you don't put an extra negative sign in there. We treat it as a voltage drop. And all of these get treated as voltage drops when inserted into Kirchhoff's law, unless you know specifically that you're going against the direction of the current. And that's only applies to a resistor. And that's never come up in the AP exam, so I don't have to talk about it. Now, I should, at this moment, just tell you to solve this differential equation. Because we created the differential equation, but once we have it, it is no different from any of the other differential equations we've had to solve in here. And I should just be able to say to you guys, do so. Assuming these are our starting parameters, find me I as a function of t. You should be able to do so at this point. And it should take you about 3 minutes, maybe 4. And since I'm assuming you're not going to break out your textbook and look it up or go online, and if I see you peeking, I will be frustrated, see if you can get the answer. I will tell you what the answer is. See if you can get to it. It's good practice, and I think that you guys should be able to get to where this leads us based on what we've been doing in this class all year. This is the answer. So see if you can solve the differential equation and produce this. Let's start with our differential equation. And I'm going to solve for L di dt, like so. You have a series of steps, and what I'm hoping is that once you've done this once, every one of these has been the same. So there is that concern that you don't have it up here. This is something you can nearly memorize. Nearly. There are parts of it that you can't. But the first thing you have to do is isolate the differential. At least that's the way I like to do it. There are alternatives, but I'm going to isolate the differential. Now you have to separate the derivative. That's the whole name of this process. So I have di over dt. I'm going to multiply both sides by dt. Well, now you have to collect terms. And terms that have t in it must be on the side with dt. And terms that have I in it must be on the side with di. And I will throw out that reminder that's just here to make myself feel superior and to make certain students feel inferior. We haven't done any calculus yet. Every bit of this is algebra 1 or 2. Right? All these rules. In fact, I think the only rule I've really used here is the additive property of algebra and the multiplicable, that one of algebra. Sure, no, that's not the right word, but way to try. Now, the next part of this process is for me to take the integral of both sides. Now we're going to do a little bit of calculus. And when I do, I like to do this process one way, but your calculus teacher, if you have one, has taught you a different way. And I like to set my limits now. At time 0, we have current 0. So I set the upper limits to just be some future I and some future t. Now, this is E and M, so I'm not going to prove that the left side is t minus 0. I'm not. It's the right side that matters, though. I am going to make the right side a little easier for it. Easier is the wrong word. I'm going to try and simplify it as much as possible to make the right side have the least amount of components that I have to deal with in my integral. So I will factor out the L and have 1 over e minus IR di. Now, there's a variety of ways to integrate that. And by variety, I mean 2. You could look it up on the integral chart. This exact integral is actually in your integral chart that's given to you on the exam, telling you what the antiderivative is and everything. So if you don't want to actually learn the process, don't. Just pull out your equation sheet, because it will have on it this antiderivative. But I'm going to use u sub, which means I take what I think is going to be the part of the relationship that I'm going to substitute for. This is what I want to substitute for, everything in the denominator. And the reason is because I have memorized what the integral of 1 over u is. That's why you try to do u sub, to reduce your integrand down to something you recognize. However, you can't just replace the integral with something about u, since u is dependent upon I. So you also have to replace di with du. So that means you take the derivative of this with respect to I. And I get negative r is my derivative. And now solve this for di. And now you have all the pieces necessary for your u substitution. So I'll have L times the integral. I'm leaving the limits out for a moment because I'm doing a u sub, and the the limits are for I, not for u. I'll put the limits back in after I complete my substitution. So 1 over u, and for di I will use negative 1 over r du. Negative 1 over r is a constant, so I'll factor it out. And now I have the more simplified integral of 1 over u with respect to u, of which we have a known antiderivative for this. And that antiderivative is the natural log of u. Now, I would probably be combining steps here to try and make this go faster, but we need to now return to our original function by subbing back in our original function and our limits. You have to apply your limits. And let me remind you, I'm trying to be incredibly explicit. I would hope that most of you are skipping some of these steps just to make it faster, because you only have so many minutes to do this, and they're only giving you a few points to do it as well, which is why on the monitoring exam it tends to tell you this is what your answer should look like. And because we know where the future of this is going, in that we are going to be solving for I, we probably want to combine this to make it easier. And now I'll bring in my left expression, which has been t the whole time. All right, so that's the calculus. The calculus is done. Any questions? Now you have to solve it for I. So to solve for I, the first thing I'm going to do is multiply both sides by r over L. Again, being way more explicit than I would like to be, but I'm trying to help all of you who are not good at this. So take me up on it. And if you don't know what each step is, if you want to do better at this, and you want to, say, Mr. Shelton, I'm really trying, why don't you write to the left or right what it is we're doing? Because when we're done, all you're going to have is that. And if you're going to have to retrace your steps, good luck. So all this extra talking isn't to give you an opportunity to yawn. It's for all of you who need to be able to write down in there, why did he do that? Well, the first thing I'm going to do is get rid of the natural log. E to the minus r over L times t equals E minus IR over E. You're solving for I now, so I don't feel any need to kind of take it easy and go slow. all the algebra. So it's just algebra from here to here to isolate I. And there it is. I'll give you an extra couple steps for those of you who are still trying to figure it out. Should look familiar. Real familiar. The charging time for a capacitor. I mean, there's a difference. R and C are in the denominator for the charging time of a capacitor, but R is in the numerator in the charging time for an inductor. So changing the resistance does have a different impact on how long it takes. You're confused about how I got this here? I'm subtracting 2 natural logs, so I can write it as a quotient.
Where'd you get that? Where'd you get the limits from?
When I apply the limits here, I have natural logs of e to the minus IR. Where did I get the limits from? To this. The first question I would have for you guys is you need to be able to tell me, does increasing this make it take longer to reach its max? Or does it take less time to reach its max? Noticing where it is, will it take longer to reach the max? And if you don't understand why this works, you should try it. You should try putting different numbers in. Or maybe make a quick graph of it with something in there and see what happens as the number in front of t gets bigger or smaller. Because in this circumstance, when we were talking about an RC circuit, the time it took for the system to reach full charge was dependent on C and R. When we think about it, when you try and rationalize it, a larger capacitor holds more charge. Does it make reasonable sense then that if C gets bigger, it might take longer to fill it up? C in the denominator seems to cause that. And if there's more resistance in the circuit, would it make sense that the charge would be traveling slower to get to the capacitor? And therefore, that would also take more time for the circuit to charge up. Do those make reasonable sense? Because it plays out different in the inductor. In the inductor, clearly, if the inductor is bigger, it takes longer to reach the maximum current. It's an inductor. It's resisting changes to the magnetic field more vehemently because it has more inductance. And therefore, it takes longer for it to reach full current. R in the numerator, I think, is a little weird there. And that might be causing you some trouble. But I want to call your attention to this, just for a quick moment. The rate at which the EMF exists, or how big the EMF is, depends on how fast the current changes. A larger value of R means that the change in current is less, and thus this back EMF is also less. That's why having R in the numerator will make it take less time to reach full current. It also is because full current is a lower value. If there's more resistance in the circuit, your maximum current will be lower than the amount of current there would be if there's less resistance. So R in the numerator here means that your max for the current will be a lower value, and that's why it shows up there as well. Right? This whole term is the max current of the circuit. If you didn't know that, you should know it now. Right? Ohm's law is all that is. So these are incredibly similar. They'll have a similar structured graph. It's important to me that you now take another step. Go back and look at your circuit and try and understand what would happen to the potential difference across the inductor and across the resistor from time equals 0 to some time in the future. You should be able to figure that out. And if you can't, I'm willing to wait a few minutes. But it's here, and I want you to consider going all the way back to our start, or try to. This is our circuit, and at time equals 0, this is what's happening to the current. So, can you tell me the voltage across the resistor at time equals 0 and the voltage across the inductor at time equals 0? And then I want the voltage across the resistor after a long time has passed and the voltage across the inductor after a long time has passed. Talk it out with the people around you. Be able to answer my question, or at least be willing to be subjected to me asking you. I'll give you like 2 minutes to talk this out with the people around you. I've just explained why it's easier to do this from the standpoint of the inductor. I'm sorry, the bell distracted me. I just explained why it's easier to do this from the standpoint of the resistor. But if you want to do it from the standpoint of the inductor, do you realize that's what you would had to have used? And you would have had to have started by taking the derivative of the current function and plugging it in here. Now, I'm asking you to do that this evening. Also, I'm going to ask something else. And that'll be fine while you're packing up, but you should listen to me while you pack up. There's only energy stored in the inductor while there is current. That's clear from this, right? That there's only energy in the inductor while there's current, because there has to be a magnetic field inside the inductor. That's where the energy is stored. If I open this switch, the current stops immediately. So unlike a capacitor, which I can disconnect from the circuit and it stores the energy is only here while the circuit is connected. How do you get the energy back out? I can't disconnect it and connect it someplace else, like we do with capacitors. We're going to have to figure something new out for how we deal with inductors. And there's a solution here. It's just not as maybe convenient as a capacitor, which is static. You can store it and move it from one place to another. Can't do that with an inductor. All right, goodbye.